Thank you. Thanks, everyone. It's great to be here. There's a couple of seats up front if people want to. So as Rachel's introduction alluded to, I'm a theoretical astrophysicist. What that means is I don't actually know how telescopes work. I don't know the constellations very well. Instead, I use the basic laws of physics to try to unravel a wide range of phenomena in the universe, from understanding black holes and neutron stars, which is central to today's talk, to other problems like understanding how the universe went from the Big Bang to all the stars and galaxies we see around us today. So I've been doing research for about 25 years now, and the stuff that I'll tell you about today is certainly personally the most exciting research that I've had the good fortune to be part of. And so what this really is about is a story of how the development of a new type of telescope, a telescope that sees not light, but gravitational waves, not only gave us a new view of some of the most exotic objects, black holes, neutron stars, but also solved some long-standing problems about where the basic building blocks of matter here on Earth come from. Where does all of the stuff that we're actually made from come from? So what I want to do is I want to start, unfortunately, by taking you back to high school chemistry. So I actually didn't do very well in high school chemistry or college chemistry for that matter. I did much better in physics, where things are boiled down to a few laws and you build everything up from that. But hopefully, if you've either seen Breaking Bad and remember what these boxes are supposed to represent, or perhaps even remember from high school chemistry, quite remarkably actually, everything that we know of here on Earth, from the food we eat, the cars we drive, the Earth itself, is built out of a few fundamental building blocks. And in chemistry, we organize those building blocks into what's called the periodic table that goes from simpler, smaller elements like hydrogen and helium, lithium, beryllium, carbon, to heavier and heavier elements, exotic elements like unanillium, berkelium, californium, which are real elements, uranium. In physics, we break these down even more. We say the fundamental building blocks of matter are actually neutrons and protons and electrons. For the most part, we're not going to worry about that. We're going to be thinking about things from the point of view of chemistry today. So one of the great triumphs of physics and astrophysics in the last century has been that we can actually tell you in a fair amount of detail where each and every element in the periodic table is primarily produced in the universe, right? These weren't here from the beginning of time. These elements have been forged in a variety of different astrophysical environments, produced and then eventually incorporated into stars and planets in the solar system. And in broad brush, that story is that the light elements, hydrogen, helium, lithium, are produced very, very early in the history of the universe, around the time of what we call the Big Bang. But really everything else, the carbon in our bones, the oxygen we breathe, the iron in our blood, all of that is forged by processes in stars. Nuclear fusion in stars takes lighter elements and builds up heavier and heavier elements over time. This is the origin of the light from the sun today. Hydrogen at the center of the sun is being fused to helium. That releases heat, which keeps the sun hot, which produces the light of the sun, which keeps the Earth hot, which produces life on Earth. Right? So that fusion process of building up heavier and heavier elements is the origin, we think actually, of almost everything in the periodic table except the very lightest elements. And there's obviously a lot of details here. In some cases, it's kind of titanic explosions of stars that produce some of the elements. In some cases, it's like the sun today, kind of long billions of years of fusion that build up the elements. But this basic distinction organizes our understanding of where the elements in the periodic table are produced. And so we think literally, right, the heavy elements here on Earth and in the sun were produced in previous generations of stars. They were spewed out into space by outflows and explosions from stars, and then eventually made their way into the gas cloud that collapsed to form the sun and the Earth. So that's kind of the history 4.5 billion years ago of how we got the carbon, oxygen, and iron that are here today. But for 75 years, there's been a kind of nagging mystery that actually a lot of this story we haven't understood very well. In particular, the heavier elements in the periodic table, not all, but a lot of the ones that I've put in red rectangles here, a lot of those we haven't understood where they actually come from. And that includes things like uranium, gold, platinum, more exotic elements like berkelium and californium, which have actually never been directly seen in nature, have only been produced in experiments on Earth, originally at the Lawrence Berkeley National Lab, which is why they're named berkelium in California. So what's really amazing is that this mystery of where all these heavy elements in the periodic table come from, this mystery was solved in a way that you wouldn't guess. It was solved by building a new kind of telescope that sees a new kind of wave, not light, but these gravitational waves. And that connection between how building this new kind of telescope that sees the universe in a new way, how that solved this problem of the mystery of the origin of the elements, that's kind of the major theme that we'll go through this morning. So I want to start by reminding you what light is before we talk about a new exotic type of wave associated with gravity. I want to remind you about light. And in fact, almost all of the information that we have about the universe comes by either seeing light with our eyes or building telescopes that see the universe in different types of light. Light actually comes in a wide variety of different forms. We call different types of light by different names, but it's actually fundamentally the same thing. So light, we think, is a wave where there's an electric field and magnetic field that change in time and move through space. And those waves are characterized by what we call the wavelength, basically how long does it take in time or space for this pattern of changing electric and magnetic field to repeat. If the distance or time is very short, we call those gamma rays or X-rays, exactly what the dentist or doctor uses to see through your body. If the wavelength is a little bit longer, we call those ultraviolet light or visible light, the light that you can see with your eye. A little bit longer than that is infrared light. So if you ever have put on night vision goggles, you're seeing the glow that objects produce in infrared light. At even longer wavelengths are radio waves. So for those of you who remember a time before iPods, we had to get our sound from boom boxes like this. Those captured radio waves and converted them into sound that we can hear. And remarkably, just by looking at light in all its amazing manifestations, we've been able to figure out an astonishing amount about the universe that we live in. And that really is an amazing fact. Just sitting here on Earth in one place in the universe, looking up at the sky and all these different kinds of light, we learn an astonishing amount about the universe. And part of the reason for that is when you look at the universe with different kinds of light, you see completely different things. So these are three pictures of exactly the same place in the sky, exactly the same object, but in different types of light. This is a picture in the radio. This is a picture in light that your eye can see in the middle, and on the right is a picture taken with a telescope that can detect X-rays. Same object, same thing in the sky, same place in the sky, same time, right? But yet you see a fundamentally different view of the universe. In this case, you're seeing that there's a black hole at the center of this region that's spewing out matter into its surroundings in the form of these jets of matter and energy. In the central image, you're seeing light from billions of stars. Each of those objects is actually a galaxy with billions and billions of stars. And on the right, what you're seeing is that between the space between those galaxies, it's not empty, which is what it looks like in the middle picture. Actually, between the space between those galaxies, there's a huge amount of matter that shines in X-rays, not in visible light. And so this gives you a feel for how, over really in the last century, as we've moved from having telescopes that only see visible light to having telescopes that can see all the different myriad kinds of light in the electromagnetic spectrum, we've been able to unravel all of these different mysteries about the universe. And in some ways, the story that I'm telling you today is a continuation of that. It's a continuation of that where we're not looking at the universe now in light. It's not a new kind of light we're using. It's a fundamentally different kind of wave, a wave associated with gravity instead of a wave associated with electricity. So what then are these gravitational waves that have now been detected and have given us this new view into the universe? So this is an animation of two objects orbiting around each other due to gravity, sort of like the Earth going around the sun. The sun actually moves a little bit because it's tugged by the gravity of the Earth and Jupiter. This is more extreme. The two objects weigh the same. And because they weigh the same, they're each moving a lot in this dance due to gravity as they orbit around each other. Now, if you imagine you're somebody in the back of the room looking at these two objects going around each other, how do you find out, how is it communicated to you that gravity is changing in time, that these two things are actually moving around, that they're not just sitting still? And the answer is that there's a wave that is sent out from these two objects, a wave that is due to the fact that gravity is changing in time. It really is literally a wave of changing gravity. And that's illustrated in this animation here. These ripples are meant to represent regions where gravity is a little stronger, a little bit weaker, a little stronger, a little weaker. And that pattern repeats itself as these objects move around each other. And these are literally these gravitational waves that we're talking about today. They're produced when there are regions where gravity is changing because things are moving around and the gravitational tug and pull that everything produces on everything else isn't static in time, but is changing in time. You'll often see these referred to as ripples in space-time. The reason for that name is actually due to our modern understanding of gravity. Our modern understanding of gravity is due to Einstein. According to Einstein, gravity is actually a property of space itself, and what's actually changing as things move around is actually the structure of space and time itself. And these waves are then small changes in the structure of space and time itself. That's a slightly more nuanced understanding. For the purposes today, I think this kind of intuitive idea of gravity changing in time because things are moving around and the gravitational pull is changing, that's actually adequate for understanding most of what we'll talk about.
So these things give off these gravitational waves and constantly they send out energy. The system is losing energy and has to spin out.
Yes, we will get to that in just a second. So I'll come back to that point in just a second. Yep.
So all these waves changing gravity.
Yep.
Is that different from light? I never thought of light waves as waves of changing light.
So light waves are waves of changing electricity and magnetism. That's right. Yep. And so in that sense, it is very analogous. That's exactly right. And the difference is if you have objects moving around that have charge, then they produce light. If you have objects moving around that have strong gravity, they produce waves of gravity. Okay. So this is kind of the idea of what these waves are, and you can see how they might be produced if you have things moving around like the Earth and the Sun, two galaxies moving around each other, like us and our neighbor, the Andromeda galaxy. Those cases, gravity changes in time, it'll produce these waves of gravity. Now, if you want to actually see a source of these gravitational waves that is strong, meaning these ripples are large and hence easier to detect, then what you want is you want objects that have a very strong gravitational pull. If objects have a strong gravitational pull and they're moving around each other, the gravity will be changing more strongly in time. These waves will be stronger. So what objects in the universe produce the strongest gravitational pull? Well, those turn out to be quite exotic objects whose understanding really goes back to Einstein's theory of gravity. So Einstein in 1916 developed his general theory of relativity, which is our modern understanding of gravity. It predicted gravitational waves, the waves we're talking about today, and it also predicted some rather exotic objects, objects like black holes and neutron stars. Those objects, we think, are in fact the objects that produce the strongest sources of gravitational waves in the universe. So what are they? Black holes are scary objects that will turn you into zombies eating ham sandwiches, as you know from every good Hollywood science fiction movie. So what are black holes really? Well, that's really a talk unto itself, but in brief, black holes are objects where gravity has won out over every other force we know of in the universe. Gravity is so strong that all of the mass collapses down to the very center of the object, producing really what is just a ball of energy. By E equals mc squared, this ball of gravitational energy produces a gravitational pull on its surroundings. It has mass, it has energy, it affects its surroundings by gravity. Neutron stars are almost as weird. They're stars, so in that sense they're a little bit more like the sun than a black hole is. They're a star, but they're a star that has the mass of the sun, but the size of a typical city here on the Earth, tens of miles big. So that means there's something as big as the sun, but 10 to the 15, 1,000 trillion times denser than the sun. And as their name suggests, when you have matter packed so closely together, the matter is not the normal stuff we're used to thinking. It's not like the sun, which is mostly hydrogen and helium. Neutron stars are made mostly of neutrons. Okay? A little bit of protons, but mostly of neutrons. These two objects are the smallest objects that we know of in the universe, given their mass, given how much they weigh. And gravity, remember, gets stronger if you have more stuff and you have stuff closer together. Okay? The gravitational pull of the Earth is stronger when you're close to the surface of the Earth than when you're further away. So these objects that are massive and small produce the strongest gravitational pull of anything we know of in the universe. And so what theorists realized really in the 1960s and 70s was that the strongest sources of gravitational waves in the universe were likely to be objects undergoing this kind of dance, but not planets, not normal stars, not galaxies, but rather these more exotic objects, black holes and neutron stars. And so this sort of illustrates what happens if you have two black holes, which you can tell, right, those are the black holes in the movie, okay? Those are two black holes spiraling around each other. The yellow and blue pattern is meant to represent this gravitational wave, the wave of changing gravity, regions where gravity is a little stronger, a little bit weaker. The bottom shows another way of looking at this. This shows kind of the strength of this gravitational wave as a function of time. So as time goes on, the two black holes get closer to each other. As they get closer to each other, gravity gets stronger, and so the gravitational wave that's produced gets stronger. So that's why this pattern gets larger, okay, the amplitude of the pattern gets larger. The other thing you notice that as time goes on, the movie seems to speed up. The things orbit faster, and this pattern gets compressed in time. The time between the regions of strong gravity, regions of weak gravity get shorter and shorter. And the reason for that is actually familiar to us from our everyday experience in the solar system. The Earth takes about a year to go around the sun, but Jupiter and Saturn and Uranus and non-planets like Pluto take longer because they're further away and gravity is weaker. So what's happening in the movie is sort of the opposite of that. As the two black holes get closer to each other, things move faster and they go around each other faster, so the pattern repeats more quickly. Okay. The question is the amplitude to scale. Since there's no scale here, yes.
It looks like the amplitude only essentially doubles when it gets.
Yeah, the amplitude is to scale, but they start very close already. In the movie, the two black holes are already almost touching, so the amplitude is actually already quite big. If the movie started when they were much further apart, the amplitude you wouldn't be able to see. It would be really small. Okay. So now to come back to actually the question you asked earlier, one of the things that should actually give you a little bit of pause about this movie is that we're generally taught in class, high school, college, whatever, that the sun orbits around the Earth happily, just goes around and around and around, and the Earth orbits around. I doubt any of us were taught that the sun goes around the Earth. We were all taught that the Earth goes around the sun. But what this movie shows is actually amazing. It shows that these two black holes don't orbit happily around each other. They get closer and closer together, and eventually they slam into each other and collide. And in that collision, they produce a new black hole. So why doesn't the Earth spiral into the sun in exactly the way that the two black holes spiral into each other in this movie? So first, why are the two black holes spiraling into each other? Well, the answer to that was basically in the question from a few minutes ago. It's that these gravitational waves are taking energy out of the system, and that energy comes at the expense of the orbit, and it causes the two objects to get closer to each other. So the honest answer, the answer that we're usually not taught in school, is that technically the Earth is spiraling into the sun by exactly the same process. The difference is that the gravity between the Earth and the sun is actually extraordinarily weak compared to the gravity between two black holes almost touching, like in the previous movie. What that means is that the Earth is spiraling into the sun, but it takes a really long time for it to spiral in. Much, 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 much longer than the age of the solar system or even the current age of the universe. So over the entire history of the solar system, the Earth is barely going to move in at all. So we don't have to worry, say, that in a few years the Earth's going to spiral into the sun, bad things are going to happen. Plenty of bad things are going to happen before the Earth spirals into the sun. The one I'm very confident of is that in 3-4 billion years, the sun is going to expand to become what's called a red giant, and in that process, it's going to totally incinerate the Earth. It's quite possible that bad things will happen before then, but this one will definitely happen well before the Earth would spiral into the sun. Question?
I've always been puzzled. I thought our perception of time, when we see a dense gravitational field in the business, is that time slows down. So I'm wondering why we can actually see those things spiral and climb ahead. When from our perspective, shouldn't time be really slow there?
Yeah, so that's a great question. So the question is related to in regions where, so just to repeat the question was, in the movie, why do we see things happening faster, given that when you're in a region of strong gravity, time actually slows down some, which is correct. So we can actually measure this on Earth. We have satellites that are orbiting around the Earth. For those satellites, time ticks a little bit differently than it does here on the Earth. Your GPS in your phone or your watch takes that into account in determining your position, that difference in the ticking of time in different regions of gravity. So what actually happens in this case is that an observer viewing far away nonetheless does in fact see the pattern getting shorter and shorter in time. So if you have a single black hole, there are kind of weird things that happen. If you have a black hole and you throw somebody into it, which I don't recommend that you do, but were you to do that, and they were to kind of try to tell you what's going on as they're falling in, depending on how you observe them, you can see that process slowing down as they go in. But in fact, they actually do fall into the black hole in a finite amount of time. This is really it's sort of like an optical illusion having to do with how you observe the process happening. So it's a great question.
So it's because we're not close by in that gravitational pairing. We're very far away, so our time frame is different than the time frame of those two black holes.
So there is an important difference due to whether or not you're viewing this close to the black holes or far away. That's right. That's not the whole explanation for this issue, but that's part of it, yes. Okay. All right, so now that I've told you a little bit about what gravitational waves are, I want to tell you about how people built a telescope to detect them. And I want to start this by just reminding you what I said at the beginning, which is that I'm a theorist, and I don't really understand how telescopes work. So I understand how to do things like calculate this, or calculate how long it's going to take the Earth to spiral into the sun, or calculate the sun's going to expand and evaporate the Earth. So to me, this telescope in particular is completely amazing that they can detect these gravitational waves. And I'll give you a sense of how hard it is, but I also want to stress that I'm really not going to do justice to how much effort went into building this telescope. So first of all, this actually is a telescope. It probably doesn't look like telescopes you're used to looking at, which are, mirrors and things like that. There are actually two of these telescopes. One is in Louisiana. There's two in the US, one in Louisiana and one in the state of Washington. And I'll come back in a little bit to why there are two of them. And there's a third one in Europe that I'll come back to as well. And these telescopes all consist of this basic structure, which is these long arms, which are vacuum tubes, which are 4 kilometers long. The original idea for how to detect gravitational waves, the modern idea of how to do it, was developed in the 1970s. The first telescope was built in 1999, and they observed the sky for a long time, 15 years, and didn't see anything. So very patient, way more patient than I am. And then what happened is, as time went on, they kept improving the telescope. This was part of the goal all along. You build it with some initial kind of level of sophistication, and you make it better and better as time goes on, so you're more likely to detect things. And in 2015, the newest version of the telescope came online, which was called Advanced LIGO. Astronomers are not really very clever in our naming of telescopes, so it went from initial LIGO to enhanced LIGO to advanced LIGO. But very soon after, actually literally in the first few weeks after the new telescope came online, they detected the first sources. So I want to give you a little bit of a feel of how this actually works. So this is a schematic showing you what's kind of inside the guts. So this here, each of those arms there represents the two arms you're seeing in the picture here. And what's actually inside those vacuum tubes is mirrors and laser light bouncing between the mirrors. So what's done is the lasers are bouncing between these mirrors, and what you can do is you can use the properties of the light bouncing over this 4 kilometer distance between these mirrors. So the mirrors here are separated by about 4 kilometers, like shown in the previous image. You can use the properties of that light to exquisitely, extraordinarily precisely measure the distance between the mirrors. And what happens is when one of these waves of changing gravity comes by, it very subtly changes the distance between the mirrors, and you can detect that by measuring the distance between the mirrors in this way. So this is, for those who've heard of it, this is a technique called interferometry that's used in a variety of different ways in both physics and astronomy to do basic experiments. This is one of the techniques that was developed actually initially that led to Einstein's theory of relativity, was an experiment using this interferometry technique. So I want to give you an idea of how accurately they can measure distances using this technique. So they can measure distances between the two mirrors to a precision that's much less than the size of a proton. Okay? A proton, remember, is the thing at the center of every atom. Protons and neutrons in the nucleus, electrons orbiting around, that's the stuff in the periodic table. So another way to think of this is that the nearest star to the Earth, other than the sun, the nearest solar system, is the Proxima Centauri or Alpha Centauri system. It's actually 3 stars orbiting around each other in the Centauri system, and that's about 4.5 light years away. And the accuracy of distance measurements by LIGO is equivalent to measuring the distance to the Centauri system, 4.5 light years, to an accuracy that's the width of a human hair. So it's absolutely mind-boggling that they're able to do this, especially to a theorist. And it really is, I think everyone would agree, this is probably the hardest basic physics experiment that's ever been done. In addition to being an astronomical observatory, it's led to the development of all kinds of new technology, a lot of interesting fundamental physics, right? This is how research often progresses. My guess is that in 100 years, some of the technology developed by building this telescope will become part of our everyday experience. It'll end up in technology just like lasers, which were developed by Charlie Towns here at Berkeley, are now part of technology in our everyday experience, even though they weren't developed for that reason. Okay, so that's, again, short shrift summary of how these gravitational waves are actually detected. So the telescope went online at the end of August 2015. September 14th, 2015, they detected their first sources, which was the collision of 2 black holes. So what I'm showing you here is sort of an artist's conception of the last stages of the dance of these 2 black holes around each other. What I'm showing you here is actually the actual data from the telescopes measuring essentially the distance between the 2 mirrors, okay? The blue and the red is the telescope in Washington and the telescope in Louisiana. And I want you to notice how similar this looks to the theoretical prediction in the movie that we saw. As time goes on, the pattern gets larger and it gets squashed. Time gets accelerated as things get closer and closer together.
What is the time frame across that?
Yeah, so the time frame across this is less than a second. So all of this action was happening in less than a second. And actually, we can use the time frame of this to measure the masses of the black holes that were involved in this collision. Okay? And the reason is that if the black holes are more massive, they're physically larger, okay? And that means the whole thing takes longer to happen. If the black holes are less massive, they're physically smaller in size, everything happens faster. So we can use the time and the scale of the amplitude of this pattern to measure that the collision of these 2 black holes involved 2 black holes, each of which initially weighed about 30 times the mass of the sun. Yep? What are the 2 squiggly lines exactly? Yeah, so what they really are, they are a measure of the distance between the 2 mirrors. They're the 2 are the 2 different telescopes, the one in Louisiana and the one in Washington. Yeah, so this is actually what's plotted is a measure of the absolute distance between them. What you're measuring, though, is an interferometric measurement. So it is a relative measurement. That's right. So, yes. No, the telescope. So you do have some idea where this happens, and we'll get back to that in a second. So I want to just briefly explain why are there 2 telescopes. So remember how incredibly small distances they have to measure to do this experiment. So it turns out that if you have a truck somewhere nearby the telescope driving by in, say, Louisiana, it will change the distance between the mirrors a little bit, and that could get misinterpreted as these gravitational waves. Or if a tree falls in the forest in rural Washington, okay, it's actually in an area where there's logging, where the telescope is, that will show up as a small change in the distance between the mirrors. You have two independent telescopes, so you can, with confidence, say this is something that happened in the sky, not something that happened randomly nearby the telescope. And that's just because this is a really hard experiment. You want this independent confirmation.
Why does each installation have two 4K arms?
So the two 4K arms are to a significant extent because that does give you some information about where they are, where the sources are on the sky. Back to a previous question, which I'll show in a second. Okay. This discovery of colliding black holes, they discovered the first one in 2015, have now discovered 6. This led to the Nobel Prize in Physics this past year to 3 of the developers of the LIGO Gravitational Wave Observatory, Ray Weiss, Barry Barish, who's a Berkeley alum, and Kip Thorne. I think all 3 of these scientists would acknowledge correctly the fact that actually the experiment was the culmination of the work of hundreds, if not thousands, of scientists. The rules of the Nobel Prize are they can only go to 3 people, and that means we tend to pick out certain people by that process as getting the accolades, but actually it was the work of hundreds of people over the course of 30 years that led to the development of the LIGO telescope. And this was actually one of the pioneering examples of what is called big science, namely that science is now not done by single people in their ivory tower, but it's actually done by very large collaborations, often international collaborations. Okay, fast forward, we've detected now lots of black hole collisions. What I want to do now is move on to really what LIGO's done just in the last year, which is detect for the first time collisions of 2 neutron stars. So there was a huge amount of excitement in the community about the possibility that LIGO would detect collisions of neutron stars and not black holes. And the reason for that is that black holes are fundamentally just gravity and energy. There's no really normal matter there. And that means that the collisions of 2 black holes can't, in any way that we can think of, produce light, because there's no normal matter involved. On the other hand, neutron stars are made of normal matter, weird normal matter, under weird conditions, mostly neutrons, a little bit of protons, but that is still the fundamental building blocks of matter, neutrons, protons. Okay? And so it's at least possible that collisions of neutron stars would not only produce these gravitational waves, but would also produce light. So there was a tremendous amount of interest in the idea that we'd be able to see at the same place in the sky at the same time in both gravitational waves and light, the same thing, the collision of these 2 neutron stars. Yep? Right, so how do black holes have a size? When we talk about the size of a black hole, it's very different than the Earth. When I tell you what the size of the Earth is, you think, okay, that's the solid crust, there's stuff there. The radius of the sun, there's stuff there. When we talk about the size of a black hole, there's nothing there. What it really is the point of no return. The radius of a black hole is called the event horizon. It's the region within which no information can get out. So it's really about communication of information, not about where physical stuff is. So you're right, it's a fundamentally different notion of what it means to have a size. Okay. So in fact, as I'll now tell you, at the same time and the same place that LIGO detected the collision of these 2 neutron stars by the emission of gravitational waves, we also saw a new source of light appear and then disappear. This faint red smudge right there, this is a galaxy, billions of stars. This is a source of light that was not there 2 days before this picture was taken. and then disappeared about a week after this picture was taken, as you can see on the image on the right, no faint red smudge. That faint red smudge caused a lot of excitement, okay? That is light associated with the collision of these two neutron stars. So how did we know where to look to see whether there was light associated with the collision of two neutron stars? That gets back to this question about, does the gravitational wave telescope tell you where the source was? And the answer is it tells you where it was, sort of, not great, but it does give you some information. And it gave us enough information to know where to look. And remember, I'm a theorist, so when I say us, I'm using the royal us. I mean my observational colleagues. So this is a picture. This is a picture of the entire sky. So think of the top here as like you're looking all the way up, and the bottom is you're looking all the way down. And this is an animation that takes us through where on the sky different telescopes told us to look at the time of these colliding neutron stars. These weird banana-shaped green regions are the regions on the sky that the LIGO telescope told us the gravitational wave source came from. So
Is that from two or from all three?
so let's go through it again. So these regions are regions actually where a gamma ray telescope, there was a flash of gamma rays 2 seconds after the gravitational wave source. We knew that those gamma rays came from somewhere on the sky, shown by those blue regions. The gravitational waves we knew came, the two telescopes in the US told us that it came from somewhere in those green bananas. Adding in the European telescope told us it came from somewhere in this region. The white circles are every galaxy in that region at the distance that the gravitational waves telescope told us this event was. What groups did is they went and looked in every one of those 50 galaxies for a new source of light at the time of the gravitational wave source. And that's how we knew where and when to see this source of light.
Why, if they only look near galaxies, wouldn't two neutron stars also exist in between galaxies?
So the question is why only look near galaxies? Couldn't two neutron stars exist far away from galaxies? So neutron stars are made from stars not like the sun. The sun will become a white dwarf when it dies. Heavier stars will collapse to become neutron stars or black holes. Most stars exist inside galaxies. So there was an expectation that it would be vaguely near galaxies. It's actually a little more complicated than that, because neutron stars actually move fast through space. They can get kicked out of galaxies. But so you'll notice it's not actually in the galaxy. It's actually a bit outside the galaxy. But it's at least somewhat near the galaxy, because that's where most stars are in the universe. Yep?
Why would gravitational waves travel at the same or similar as to the speed of light?
Yeah, great question. So according to Einstein's theory of relativity, light and gravitational waves both travel at the speed of light, or the speed of gravity. It's the same speed. Call it whatever you want. They travel at that speed. We didn't know that that was true. This is actually an experimental confirmation that that's true to an extraordinarily high level of accuracy. But what we know is we know that the two speeds are almost the same within, I think it's like a part in a trillion or so. Yep.
Was this extraordinarily lucky? I mean, these neutron stars, if they were in that galaxy, you wouldn't see them.
Yeah, if they were in the galaxy, it would be harder to see. We have techniques for what I would have shown you would not be a picture like this. Instead, had the source been on the galaxy, I would have shown you a picture where in two different images, you subtract the two images to pull out the new source of light. We still would have been able to see it in this case. It was bright enough. Yep.
So assuming that there's some regular recording of all the different regions in the sky, and then after the fact, you went and looked in those recordings, and that's what you're showing us?
So the question is, was this data all taken, would it have been taken anyway? Was it just being taken routinely? Or was it specifically taken because of this event? The answer is that we do not have complete records of the entire night sky at every electromagnetic wavelength at all times. So this actually was a dedicated set of observations that happened because the LIGO gravitational wave telescope sent out an alert that says, we just saw something cool. Every astronomer in the world, go take your telescope and try to find out what it looks like with light. And that's actually what happened. So this shows which telescopes on the Earth and in space went and looked up at the sky to try to observe this source of light. So 70 different observatories on the ground, many in space. In every part of the electromagnetic spectrum, from the radio to the gamma rays, this source was detected. A third of the world's astronomers were actually participated in this discovery, either in the observations or in the theoretical interpretation. There's telescopes on every continent of the Earth. Okay. South Pole. The South Pole is actually a great place to do astronomy. This may not make sense, but it's actually very dry, okay, despite there being a lot of snow. So this was, I think this really is and will go down in history as one of, if not the most well-studied single phenomena ever in the history of astronomy.
Okay,
Yep, go ahead.
describe a little bit of the timing. I mean, how did it start and how much advanced warning was it?
Yeah, so what was the timing? So the timing, what actually happened, so first of all, remember, this galaxy is like 100 million light years away, so this all didn't happen in August. This happened 100 million years ago, okay? We got the light and the gravitational waves in August. So the first thing that was detected was the gravitational waves. 2 seconds later, gamma rays were detected, and about 12 hours later, visible light, like in that picture, was detected. And then a few weeks later, radio waves, X-rays were detected. Right. So why is there a delay? So the shortest answer to that is that the light, when it's initially produced, there's so much matter around that the light can't travel freely out. And it bounces around for a while, and then eventually the light can get out and come to us. The delay is produced by the light bouncing around. And that'll make more sense in a second when I describe a bit more about how the light is produced. So I want to give you an idea of what does it mean for a third of the world's practicing astronomers to be involved in this event. So when I want to read a paper, I go to a website. There's a couple different ones. It's called Astrophysical Data Systems that has, digital versions of all the papers, right? I don't actually read a hard copy journal anymore. It's all PDFs. This is one of the discovery papers called Multi-Messenger Observations of a Binary Neutron Star Merger. Multi-messenger means light and gravitational waves, two different types of information, two different messengers about the universe. This paper was published in astrophysical journal Letters. Letters are the papers we write when we want to very briefly describe in a short amount of space what some new exciting phenomena. Normally, astrophysical journal letters are 4 pages long. This astrophysical journal letter is 109 pages long. It's 109 pages long primarily because if you have a third of the world's practicing astronomers on a paper, you have 90 pages of people's names, what institution they're at, and who gave them money. So that's the practical consequence of having that many people on a paper. Okay, so, yep.
How did the other observatories see it without the telescope?
How did the other,
Observatories.
so how did they know to look,
How
or?
did they see it
How
without those telescopes?
Yeah, so the way that the other telescopes saw it is they were told where on the sky to look. So basically, as kind of by the process shown in this animation, we figured out where on the sky to look, where this new source of light was, okay, this picture. We knew that that's where we should look, and then all the other telescopes, the radio telescopes, X-ray telescopes, visible light telescopes, infrared telescopes, ultraviolet light telescopes, all pointed at that place in the sky. Yeah, the 12 hours actually is really irritating. So there was a delay by about an hour and a half in initially announcing the results. And that meant that telescopes in South Africa, which could have seen this after about half an hour, weren't told until it was too late. And remember, the sun gets in the way of observing things in the sky. And so the sun had risen, and so it took 12 hours for that reason. So.
You also mentioned the gamma rays, much shorter to the event.
Yes.
So these would have been detected even if there were no gravitational...
Correct. The gamma ray telescope is sensitive to most of the sky, and the gamma ray alert actually came out first because there was this weird delay in the gravitational wave processing of the data. That's why this animation starts actually with the gamma ray telescopes. Let me hold off on questions now so we can get through the end. Happy to answer questions afterwards. Okay, so this is the source of visible light. So what I want to now tell you is a little bit about how we think the light is produced and what we learned from observing this light. And I'm going to focus, actually, we learned different things, as I've already told you, by observing different kinds of light. The gamma rays, visible light, radio waves, X-rays tell us different information about this phenomena. I'm going to focus on the visible light in particular, and the light that's a little bit longer than what our eyes can see, the infrared light. And the reason is that's the light that actually tells us about the origin of the elements. It's also the light that's the most related to my own work. So this is an animation put together by my colleague Dan Kaysen here in Physics and Astronomy based on work that we've done together that describes schematically on the right what we think the material looked like that produced the light, and then on the left the brightness of the light as a function of time in the blue, which is kind of light that your eyes can see, and the red is in this light, infrared light, that's a little longer than what your eyes can see, a little longer wavelength. So what we think happens is during the collision of the two neutron stars, most of the matter in the neutron stars ends up forming a black hole. The two neutron stars collide together, kind of it's complicated for like a second, and then the whole thing probably collapses to a black hole. But during the collision, a small amount of material is actually flung out into space. The collision does not perfectly, everything doesn't perfectly collapse down. Some debris is flung off into space, forming this cloud of material that's expanding out into space. And that cloud is shown in this animation on the right. What we think happens, this neutron star debris is initially mostly neutrons with a little bit of protons. As that debris expands out, the neutrons and protons start to combine to form not free neutrons and protons, but to form atomic nuclei. And what atomic nuclei do you form if you have mostly neutrons and a little bit of protons? Well, you form the heaviest elements in the periodic table, because the heaviest elements in the periodic table are the ones that are mostly neutrons with a little bit of protons. So neutron star debris flung out into space, it was actually realized in the 1970s, would be a great way of making gold, platinum, berkelium, californium, uranium, and all of those unusual heavy elements in the periodic table. So what we think then is this debris, very quickly, in like a second, the neutrons and protons combine to form all those unusual heavy elements, and then they expand out into space. Many of the heavy elements that are produced are initially radioactively unstable. You don't necessarily form stable heavy elements, elements that'll live forever. Many of the things you form are unstable, so they decay, just like a fission reactor. Uranium, plutonium give off energy as they decay. So what we think is actually produced by this collision is a cloud of radioactive debris expanding out into space. That radioactivity is important because it keeps the cloud hot. It produces all this heat as the stuff is expanding out, and that heat is the reason that this cloud produces a bright source of light. To produce bright sources of light, you need to be hot. That's why stars are much brighter than planets. They're much hotter than planets. In this case, this cloud of debris is kept hot by the very process of producing these neutron-rich heavy elements in the periodic table. And we can diagnose, using the properties of the red light and the blue light that are produced in this event, we can diagnose what elements, roughly, it's actually tricky, but we can diagnose roughly what elements are produced in this collision. We think this single collision of two neutron stars observed in the visible and infrared light produced over 100 times the mass of the Earth of gold and platinum, and several times the mass of the moon worth of berkelium and Californium.
And most likely it has produced elements we have never ever seen, but they will not survive very long.
Correct. So even berkelium and Californium are, every version of berkelium and Californium is unstable, and so will not survive for billions of years. There's some of it still out there floating in that cloud, because there are isotopes, as they're called, of berkelium and Californium that live longer than a few years. Well, actually, okay, because it happened 100 million years ago, there probably aren't. I take that back. Damn. Okay. And we can actually use this much mass produced in this event. How often do we think neutron stars and two neutron stars collide with each other? We can use that to figure out how much total amount of gold, platinum, uranium is produced by colliding neutron stars, and it's equal to all of the gold, platinum, uranium we think exists in the universe. Okay, that's uncertain because we've only observed one of these, okay? But it's consistent with the idea that collisions between neutron stars produce all of these very heavy elements in the periodic table. So I've emphasized this process of discovery as being one where new telescopes are built, observe new phenomena, give us new insights into the universe. And that's true, but actually science often progresses in a different way, and that was true in this case. Actually, many of the things that I described to you were actually predicted theoretically before they were observed. So in 2010, my former graduate student, Brian Metzger, who's now on the faculty at Columbia University, we theoretically decided we wanted to calculate, for reasons I can go into if people are interested, we wanted to calculate what would happen in the collision of two neutron stars if some debris gets flung out into space. How hot would it be and how bright would it be? And so we actually calculated, without it having ever been observed, what would the brightness be over time from this radioactive debris cloud flung out into space. The red curve here is a plot taken directly from our paper of brightness versus time from our predictions in 2010. And the blue points are the actual data from the detection in 2017. So this, in this particular case, thank you. We got a little lucky, okay, because this is a hard calculation. There were things that were uncertain. So I think the degree of agreement here is better than it should be. But this is a nice example where knowing just some basic physics, radioactivity, heat, hot stuff produces light, we could go through this chain of basic physics reasoning and actually tell the observational astronomers what they should be looking for and when they should look when there was a collision of two neutron stars. And that interplay between theoretical predictions and observational discovery is actually one of the things that astronomy is particularly good at. There's a great connection between the theoretical and observational advances, and it's a lot of what drives the field forward. Okay. So I want to end just by giving you some broader context for this discovery. So Carl Sagan famously said that we are all star stuff. And what he meant by that is this kind of story I told you at the beginning, that other than hydrogen and helium and lithium, everything that is the building blocks of matter, okay, the carbon in our bones, right, the oxygen in the air, the iron in our blood, all of it is produced by processes in stars. Nuclear fusion in stars takes light things, builds bigger things, and then those heavy elements get spewed out into space in stellar outflows and stellar explosions. That material that's flung out into space collects into clouds of gas. Those clouds of gas collapse under the action of gravity to form new stars and planets. And that's how the products of fusion in stars get incorporated into later generations of stars and planets. One of my colleagues, Martin Rees, puts it slightly differently, a way I actually prefer. He says that we are all nuclear waste, which I particularly like. So what we've now learned is that very literally every single one of us in this room has inside of them a little bit of debris produced by colliding neutron stars. Each of our cells actually has a very, 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 very small amount of gold in it. So in addition perhaps to the gold or platinum on your ring fingers, there's also that basic building block produced by colliding neutron stars is actually in every one of us. In addition, and in some ways I think more remarkably, it turns out that uranium is actually important for the existence of life on Earth. So you may know that the Earth has what are called plate tectonics. The plates move around. The continents aren't static in time. They're different in the past, will be different in the future. The existence of plate tectonics is due to the fact that the interior of the Earth, the mantle of the Earth, is really a liquid, not a solid, and it slowly, over hundreds of millions of years, boils. And the boiling of the interior of the Earth is due to a significant extent to radioactive heating by uranium and a few other elements. So if we didn't have uranium, we wouldn't have this boiling motion of the interior of the Earth. We wouldn't have plate tectonics, and we wouldn't have, we think, what's called the long-term carbon cycle, which is part of what keeps the atmosphere of the Earth actually breathable for us. So quite amazingly, it's not, I think, a stretch to say that colliding neutron stars and the debris that they produce, the heavy elements that they produce, are an important part of what actually makes the Earth a livable place for us, at least today. So I'll end there. Thank you. Happy to take some more questions. Yep. Yep. So the question is, the universe is expanding. Does that influence the likelihood of particles to collide? Or stars? So yeah, the universe is expanding, but the solar system is not expanding. Okay? But the sun's gravity on everything else in the solar system wins out over the expansion of the Earth, of the expansion of the universe, sorry. So the distance between our galaxy and other galaxies is getting bigger due to the expansion of the universe, but things like two stars orbiting around each other, two black holes orbiting around each other, planets orbiting around stars, those distances are not expanding, and so it really doesn't come into the likelihood of these kinds of collisions. Yep?
For a long time, as astronomers couldn't figure out where these heavy elements came from that are heavier than iron, because we know that fusion in stars can produce elements up to iron. But can't some of these heavy elements be produced in supernovae explosions?
Yeah, so the question is, if we go back to the periodic table, aren't some of these heavy elements produced in stellar explosions? And the answer to that is it used to be thought, actually, that many of these neutron-rich heavy elements were produced in stellar explosions. As our understanding of stellar explosions has gotten better, it has become less and less theoretically plausible that exploding stars produce these neutron-rich heavy elements. So that is now disfavored relative to colliding neutron stars. Some of these neutron-rich heavy elements are produced in stars. There's two different kinds of these neutron-rich heavy elements, so I've glossed over some details, but it's not actually exploding stars. It's stars actually sort of like a little bit like the sun later in its life will undergo a rare kind of fusion to produce a few of these neutron-rich heavy elements. Not the ones I've highlighted here, but some of them. Yep.
The piece that came together for me is if you go to any of the mines in the world, like where the gold exists,
Yes.
they look like something hit and drove down in it.
Yeah.
And so maybe a year ago I came to that realization that the reason they find gold in South Africa or gold in Arizona is because it was one of those exploding neutrons that came through.
So probably, well, when the Earth formed, so all of this gold out there, so I should be clear, this gold is not now like big hunks of gold, okay? It's actually in gaseous form still. So it's a gas.
Out there, but here it's in danger.
Here, exactly. So what'll happen later, as the clouds of gas get assembled and collapse due to gravity, it'll eventually get compressed dense enough that it'll become a solid. But it's probably lost most of its memory of all the details of the colliding neutron stars that it formed from. So the veins of gold on Earth and things like that are mostly geologic processes on Earth, and it's kind of lost its memory of all of that colliding neutron star stuff.
If you look at the models of mines, they look like something
Yeah.
hit and went down in
No, I don't think it's actually a collision like that. It's, yeah. Try to get some different questions. Yep.
So I heard that the first collision that affected there's like two total masses of energy created, and it was briefly more than all the other energy in the universe, something like that.
Right.
Is that right? It sounds so unimaginable.
So let me ask you a trick question, okay? So take two black holes, which initially weigh 30 times the mass of the sun, spiral in, collide with each other. What's the mass that you're left with? What's the new black hole's mass?
59.
So a good guess would be 60, 30 plus 30, okay? The answer is about 56. And so what that is, remember, why are the two black holes spiraling in the first place? They're spiraling in because these gravitational waves are taking away energy equals mc squared. That means the two black holes the final black hole has to end up weighing less than the two black holes that started the whole thing off. And they weigh less by about 4 times the mass of the sun in this particular case. That energy all comes out in about a second, okay, in the form of this burst of gravitational waves.
A question about the accuracy of the distance measurements in LIGO.
Yes.
So if the change in length is less than a proton, and you measure it with typical light, which is probably 1,000,000 times longer wavelength, and then in barometer you get length changes by phase shifts between light waves. I mean, how can they measure to an accuracy of 10 to the minus 6 the amplitude change in this interferometer?
Yes.
What trick?
So the trick is the interferometer. It's that what you gain by is related to the distance between the mirrors. So the fact that you can separate these mirrors by 4 kilometers, which is extraordinarily long compared to the wavelength of the light, means that you're actually measuring the phase shifts much more accurately than you would think. The accuracy is not related to the wavelength of light. It's much, much, much better than that by an amount which is directly proportional to the length of the distance between the mirrors. So great question. Yep.
Why do the gravitational waves not affect the light waves going between the
So why do the gravitational waves not affect the light that's bouncing between the mirrors here? The answer is that gravity is incredibly weak, okay? So the force of gravity is actually the weakest of the fundamental forces in nature. And the reason we think it's important is because everything in the universe, to first approximation, is pretty neutral, so electricity is unimportant, nuclear forces are unimportant, so gravity is sort of the only game in town for big things in the universe. But in this case, the gravitational waves have a negligible effect on the propagation of the light.
I've often wondered, is there trauma near the collision of the black holes? That is, since time and space is all uniformly changing, if you're within, let's say, a couple of light years of where that collision occurred, even with the neutron stars, would that destroy the normal matter around there by yanking it around?
So yeah, the question is, if you were close to this collision, let's take to start the two black holes where all it is these gravitational waves that come out, would that negatively affect you? And the short answer is basically no. And the reason is sort of the same reason I just gave, is that gravity is actually pretty weak. So obviously, if there was, like in Interstellar, a planet orbiting one of these black holes, okay, that is spiraling in and they collide, okay, that would be bad for the planet if it was really close to the black holes. But if you were in that galaxy when it happened, a typical place in the galaxy would not care, would not be affected.
So you mentioned the timing and the sequence of when they got the signals, and this is the first time this has happened. Have astronomers now tuned that whole process so that the next time this happens, that the signals will go out sooner and avoiding false positives and all that kind of stuff?
Right, so this process of observing something that shows up on the sky that wasn't there before and then that disappears and alerting everybody else where to look, this process has actually been honed over the last century. And it started with, you look up at the sky in visible light and you see new sources of light. Those are called novae, new sources of light, or supernovae, okay. Kilonovae, which is this new source of light for colliding neutron stars, is kind of in between novae and supernovae. So we've actually honed that process quite a bit already over the last century. Now, obviously, the new wrinkle is adding the gravitational wave telescopes into that story. And that process actually has been refined a lot over the last 15 years. Remember, they've been taking data without detecting anything for a while. So the process already was refined, and it'll continue to be refined, absolutely. I think the kind of lucky thing is that process was actually pretty far along already. So this went extremely smoothly with this one hiccup that the gravitational, what actually happened is sort of at one of the gravitational wave telescopes, there was a huge, weird glitch in the data, like a tree falling or a truck going by or somebody shooting a shotgun at the Louisiana telescope, which happens, right? That produced this weird spike in the data that confused them for a while. It was almost at the same time as the signal. And so that is what confused them for a while. So they didn't know something interesting was happening. It took them an hour to figure out that something interesting was happening. Yep.
So, I never knew before today that there were different generations of stars, but I'm guessing what this all means is that any star that has a solar system around it that has planets would have to be like a second generation star. My question is, are there any first generation stars still scattered all over the place?
Yeah.
Or just have like hydrogen?
Yeah, that's a really great question. So this is something that people look for. So the expectation is that the very first stars that ever formed in the universe, because the Big Bang was hydrogen, helium, lithium, the first generation of stars should have hydrogen, helium, and lithium. Now, they do fuse as time goes on. They fuse heavier elements, but initially they should just have hydrogen, helium, and lithium. And so people look for stars that have very few heavy elements. And we have found stars that have less than 10 million times the amount of heavy elements that the sun has. But we've not found a star that has no heavy elements. Probably that's just a matter of time. They're rare, they're hard to find. It could be that none of them are still around today. Namely, it's possible that all of the first generation of stars were massive, and so they go through life fast, and so they're not still around today. That's the uncertainty. So definitely, this is actually a very active area of research, and we found stars that are clearly very old, very close to the first generation, but not exactly the first generation. So.
But could we still see the light from those first generation stars?
We could. The problem is just knowing which source of light in the sky to look at. So you have to sort of get lucky. So people survey the sky. What you do is you don't look where the sun is, because where the sun is, the stars are sort of like the sun. They have a lot of heavy elements. You look far away from the center of the galaxy and the outskirts of the galaxy. Those stars, on average, have less of the heavy elements.
Is there any particular reason why black holes and neutron stars would seek each other out?
So why is it that black holes and neutron stars end up orbiting around each other, getting closer, et cetera? So I think the short answer to that is that most stars in the universe are in orbit with other stars. So the sun having just planets, not a companion star, is slightly unusual. So most stars have other stars orbiting around each other. That means massive stars, which become neutron stars or black holes, occasionally you'll end up with two neutron stars orbiting around each other. Most of the time, those two neutron stars orbit so far apart that it takes much longer than 13.8 billion years, the age of the universe, for them to spiral in. But occasionally, the two neutron stars orbit close enough to each other that they will collide in less than the age of the universe. So, yep.
Last question.
Yep.
Let you go.
What's the statistical distribution in the universe of heavy elements?
Do you mean like what, do most stars have an amount of heavy elements sort of like this?
Relatively unique in having all these heavy elements, or
Right. So the question is the sun unique in how many heavy elements it has? And I think to kind of step back even more, the existence of the planets, and hence the existence of life, requires those heavy elements, right? The Earth is mostly those heavy elements. It's not mostly hydrogen and helium. Hydrogen and helium are rare in the Earth. They're common in the sun. So the sun formed 4.5 billion years ago. Most stars actually formed a little bit further in the past, maybe 9 billion years ago or so. So the amount of heavy elements that the sun has is a little bit less heavy elements than the sun, but not by a lot. So.
So is there a LIGO